Hey, what's up, guys? Okay, so today let's talk about a final theorem, called the law of total covariance. Basically, previous I proved the law of the expectation value, total expectation value, and the law of total variance. If you haven't seen it, you can check out my previous video. Basically, the technique is very simple. Just expectation of x equals to expectation value of x, y. And then notice that these guys are random variable on y, so we take expectation value, we only care about y. Oh, by the way, this notation is very important. Okay. Okay, so theorem is the covariance of xy. It's just give you a very simple. So expectation of xy minus expectation of x, expectation of y. Okay, in terms of joint probability, hopefully this definition is understandable. Okay, so all we need to prove is the following. So by the way, this should be just a simple definition. Okay, so all we need to prove is the following. It's basically the covariance of xy is the same as the expectation value of covariance of xyz. So this is another variable, and plus covariance of expectation value of xz and the expectation of yz. Okay, so conditional. So this guy, I should understand this guy is a function of z. So when I take covariance, I understand these two are function of z. Sorry, function of two z, right? Okay, and I understand this guy also by the same definition. And yeah, so this is the results that we are going to prove. And let me just talk about notation. So expectation value of covariance of x, y, z, right? By definition, this is by definition, right? It's basically the expression of x, y, z minus expression of x, z, and expression of y, z. Just everything is conditional z. Okay, so let's do the proof. So we can write the covariance of x, y, expression x, expression of expression of xy, right? Xy minus expression of x and expression y. Okay. Now I can use the trick, right? I can just write expression of x, y, z, and minus expression of x, z, expression of y, z. Okay, so now this guy, right? This expression value of x, y conditional z. This guy, right, I can just replace. Okay. So I'm very good on replace everything. So I get the exponential value of covariant x, y conditional z plus exponential of x, z, and exponential of y, z minus exponential of x, z, exponential of y, z. Okay, so this turn, and this turn. Okay, and by something, right? By something. Sorry, there's a note here. Sorry, I'm stupid. There's just definition. Okay, so this guy, the first term is the expectation value of covariance x, y conditional z. And then we got three expectation value, right? We got three expectation value of x, z, expectation value of y, z, minus expectation value of x, z, expectation of y, z. And oh, by the way, I forgot about expectation here. So I should put expectation here and expectation here. Let me just write carefully. I guess my derivation is so quick that right, I miss something. Okay, so what I want to say is that in this part, right, I should write it as expectation of xz and the expectation value, right? So each term has two expectation because I use the law of total expectation value. Okay, so I did this. And for this one, I should have two of expectation value. Okay, expectation value. Okay, if you see carefully on first term looks good, right? First term looks good, the same. The second term, right? You can see if I tell this guy random variable, this guy random variable, this guy random variable, this guy random variable, let's say x tilde, y tilde, x tilde, y tilde. Then all these four terms looks like a expectation value of x tilde, y tilde. minus expectation value of x tilde and times expectation of y tilde. So expectation of x tilde y tilde minus expectation of x tilde and expectation of y tilde. Also combine these two, that by definition, these guys are covariance of x tilde and y tilde, which is exactly this term. Okay, so this is basically the proof, right? The proof is just the basically the same tool, let's say technique, as the total variance and the total of expectation value. And that's it. See you guys next video.